Okay, so hi everyone, this is the tutorial 2 or the tutorial for the assignments given for week 2 of this course Newtonian mechanics. Right, so we will go by the problems one by one, and I'll give you the way to solve the problems, or mainly as much as I have seen that this week's problems are mostly conceptual, not too much mathematical. So we'll try to read those problems and try to understand the concept behind solving them. Okay, so that you can be able to understand and decode similar problems when you are given in that you will be given maybe in future assignments, or let's say in exams. Right, so let us start then. So question number one is an automobile of mass 1500 kg is moving down a 10-degree inclined road at a speed of 80 km per hour when the brakes are applied, causing a constant total braking force of 7500 Newton. The car is interacting with the earth, the road, and the air. Below are some statements about application of Newton's third law to this problem. Identify all the false statements. Okay, so first of all, let us register what the problem is giving us as an information to solve the problem, right? So we are being said that a car, that is the automobile basically here, that there is basically this car, let's say. Okay, so assume this is the car. Now this has a mass of 1500 kgs, right? And so although right now I have drawn it on a like flat plane or surface, right? But sorry, no, I just, yeah. So right now I have drawn it on a flat surface, unlike the thing that is given in the question, that it is moving down a 10-degree inclined road. So the car is moving down like this. So let's say this is 10-degree angle, right? So this is your flat surface, and with respect to that, at an angle of 10 degree, there is this inclined plane. Sorry, this inclined plane. Okay, so this is the inclined plane at 10 degree, and on this the car is actually moving. So car is sitting not on a flat surface but on a 10-degree inclined plane with respect to a flat surface, right? Now its mass is again 1500 kg, and it is moving down the road. So basically the car is trying to move down this inclined plane, and its speed is given as 80 km per hour. So you know that speed is a scalar quantity, so it has only magnitude and no direction. But if you talk about velocity, then it will have both magnitude and direction. So the magnitude part will be same as the value given by the speed, which is the scalar value, right? So the velocity vector for the car here will have a magnitude of 80 km per hour. And for the direction of the velocity vector, we have to identify it by this arrow mark. For this case, this is along this plane, down the plane. So this is the velocity vector, v vector, I will say, for the car. And at this condition, when the brakes are applied, I mean somebody that is driving the car is trying to stop the car by pushing on the brakes, then it causes a total braking force of 750 Newton. So basically, instead of moving down continuously across continuously down the inclined plane, you want the car to stop midway, and so you push the brake. So the braking force will basically, what will it do is that the force will try to drag the car so that it does not move farther down the plane. So basically the force has to be in the opposite direction, right? So the braking force, whatever this braking force is, has to be in the opposite direction, which we call by F subscript B. This is the braking force that you apply to stop the car. This is 750 Newton. So now in this case, you are asked that the car is interacting with the earth, the road and the air. So you know that the car is sitting in the whole environment. So the environment will always always have an effect on that car or anybody that is basically sitting on that environment. So in the same way, the car will have effects from the road on which basically this inclined road on which it is moving. Okay, so this is the inclined road, right? So this will have an impact, this will have a force acting on the car because the car is in contact with this plane, and then it will also have forces from the earth, basically because this road is sitting on the earth, right? So the earth will have a impact or effect. I'll say impact will mean something else. So the earth will have an interactive effect on the car, as well as the air, because the air is surrounding the car environment. So basically air will also have a force or a interaction with the car. Now you are asked that you have to apply Newton's third law for this problem and identify which statement is true and which statement is false. So first of all, if you just think about what Newton's third law stated, that is very simple, right? That every force for an object will have a pair force or a partner force which is just equal and opposite to the main force, right? Or you can say in other words that every action has an equal and opposite reaction. Okay, so that means if there is a force acting between two bodies, and if one body is acting a force or giving a force on the other body in some particular direction, then there will always be a partner force or a couple force to that, which will basically be created or basically be applied on the first body by the second body in just the opposite direction, but they will be of the same value. So that is the Newton's third law. That third law of Newton basically states that every action has an equal and opposite reaction, right? Okay, so basically if you have if you have this body, let's say this is your body 1, and this is in contact with another body which is this below plane, which is body number 2. So in this case, by following Newton's third law, if body 1 is applying a force, let's say F1 on body 2 in this downward direction, because of obviously there will be a gravitational force or a weight that it will be applying on the surface, then there will be an opposite force that will be applied by body 2 on body 1, which will be in this direction. Okay, so do not get confused even if I have drawn the arrow to be longer, but that does not mean anything physically. It's just for convenience, because I did not want to draw any further on top of this. It will be messy. So that is why. And we call it F2, that is a force 2, that is the force the body 2 applies on body 1. So by Newton's third law, if that is true, then F1 will be minus of F2. So basically their values are same, but the directions are different. Basically force vector, because force is a vector quantity which has a direction. So in that case F1 vector is minus F2 vector, but their magnitudes will be the same, because mod of F1 vector will be mod of F2 vector, because minus sign does not matter when you take the modulus or the magnitude, right? So this is an equal and opposite force. So equal, opposite, partner force exists for each force. This is the Newton's third law. So basically this is simple. Now you have to consider how to apply it in this problem, that is problem number 1. So let us read the options one by one, and then we'll understand which one is true and which one is false. So number 1 is, according to Newton's third law, the force by the earth on the car is equal and opposite to the force by the car on the earth. Okay, so if you read it carefully, that it is saying that the force that is applied by the earth on the car and the force that is applied by the car on the earth, that they are basically equal and opposite. So this is basically true as per the Newton's third law. Why? Because here the objects are same in both the cases. Earth and car, these are the two objects, right? Now once they are saying that the earth is applying force on the car, and for the other case the car is applying force on the earth, and they are equal and opposite to each other. So basically that holds the Newton's third law actually correct, because between two bodies, earth and car, or between two things, earth and car, the force that is acting in between them is actually, they are partner forces, they are equal and opposite to each other. So this is true. Now option number 2 says, according to Newton's third law, the force by the earth on the car is equal and opposite to the force by the road on the car. So this is not true, or this is false, because in the first case you see that the force is acting between the earth and the car, that is earth is applying a force on the car. But on the second case it is saying that the road is applying a force on the car. So they are not partner forces, because they are not acting between the same two bodies, in the sense that once they are between earth and car, and the second case they are between road and car. So even if it is saying that equal and opposite force, but they are not definitely partnered forces, so this is not holding the Newton's third law true. So this one, first one was true, second one is false. Then the third one says that according to Newton's third law, the contact force by the road on the car is equal and opposite to the force by which the car pushes down the road. Now you see that this one will be correct again, because again two similar bodies are taken, once their road and the car. So in the first case, the road is applying a force on the car because of the contact between the road and the car. So between the road and the car there is a contact force. Now it is equal and opposite to the force by which the car pushes down the road. So as the car is moving down, or car is pushing down the road, so it will also apply some force on the road, otherwise how can it move down the road? So in that sense it is saying that they are balancing out each other, they are equal and opposite to each other, which is exactly what Newton's third law actually states. So this one is also correct. And fourth one says that the application of Newton's third law requires the knowledge about the angle of inclination of the road and the coefficient of the friction. This is definitely not true, because Newton's third law does not care about what is the angle of inclination, what is the road condition, what is the coefficient of friction value. These are not important, because you just have to simply know that so you have to identify all the false statements, right? So just give me a second. Yeah, this is just 1 second. Just let me check something. Okay, so right, I have, let me, okay, yeah, so yeah, go to full screen. So yeah, as I was saying that Newton's third law, it does not require the knowledge of the angle of the road or the coefficient of friction, because you see that it is independent or irrespective of that. You just have to know that two bodies are there and they are like applying some force on the other. And Newton's third law says that they are basically partner forces which are exactly equal and opposite to each other. They are equal in their magnitude, and the force vectors are opposite in direction to each other. So you do not need all these information of theta, or that means the angle of inclination, or the coefficient of friction. So this last statement is also incorrect. So if you have to identify all the false statements, then it will simply be option number 2 and 4, they are incorrect. So you have to choose this option. Okay, so this was simple. This is done. Right. Now, okay. So question number 2. According to Newton's second law of motion, net force acting on an object causes change in its, what are the out of the four options is true, you have to choose. So first of all, what is Newton's second law of motion? Just quickly let us remember that or recapitulate that. So Newton's second law of motion states that if you apply a force on a body, then it will cause acceleration to the body, in the sense that it will produce a change in the momentum of that object with time. So basically your force that is applied on the object is equal to dp vector by dt, which is the rate of change of momentum of that body with respect to time. So this is your force, right, and this is your rate of change of momentum of the object, right? So in other terms, you know that what is momentum? Momentum is nothing but your mass times velocity v, right? So if you just replace it here, so it will be d dt of m times v. Now you know that mass is not a vector quantity, it has simply a value, so it is a scalar. But velocity is a vector because it can have both value and direction. And the mass of that object is fixed, right? It is not changing with time. So whatever is changing is the velocity. So then m times dv by dt it is. So basically your force vector becomes dp dt, which in turn reduces to this term m times dv vector by dt. So that means your velocity of that object is changing with respect to time whenever you are applying a force on that object. So this can also be written as m times acceleration, which is the acceleration a vector, where a vector is acceleration is defined nothing by but the rate of change of the velocity. Okay, so if you are applying a force, its velocity is getting changed with time. So for a constant force, it will have a constant rate of change in velocity. That means dv dt will have a fixed value, and therefore acceleration will have a fixed value. So basically, if you are not changing your force, if you are continuously applying the force, it will not anyhow change the like acceleration value will be fixed. Only dv dt, that means dv dt will be fixed. Okay, so that basically dv dt is some constant value, let's say c, some constant value, let's say c, because the force is fixed. You are applying a force and you are causing a rate of change in velocity, either an increase in velocity or a decrease in velocity, but that rate of increase or decrease is constant, or dv dt is constant. That means the acceleration a is constant. The only thing that is changing is v, because v is now c times dt. So whatever is the rate of change of velocity c, and for a fixed given amount of time, let's say you are starting from t0 and you are going up to t1, and you want to see how much is the velocity that is being, the value of velocity is getting into once you apply the force for t1 time and you basically change your velocity. So final time t1, what will be your velocity? So initially let's say your velocity was 0. Okay, so then your v will be like c dt, so that means c. So if you just integrate it, then it will be like ct, taking the limit from 0 to t1 plus some constant. Now if you assume that your at t equal to 0, or at the starting or initial time, the system did not have any velocity, or it was at rest. That means at t equal to 0, v equal to 0. So when you put that in this equation, so this is c t from 0 to t1, that means it is c t1 minus 0 plus constant, right? But for this case, if you say that at t equal to 0 your velocity was 0, that means v equal to 0 at c 0 minus 0 plus constant. So when it is multiplied by 0, obviously your constant terms reduces to 0. That means your only equation that you will need in this case is simply dv dt is equal to constant, and you are getting, and your condition given is at t equal to 0, v was 0 starting from rest. So then there was no initial velocity to start with. So basically after t time, at v at t, velocity at t will be simply c times t1. So at t1 time stamp, the velocity will be the constant times t1, right? So basically your velocity is the quantity or the thing that is changing for that object with time when you are applying a force on it. So this is the Newton's second law. So you can apply here and you can say okay, so yeah, the question was net force acting on an object causes change in its not position but velocity. Acceleration will also not get changed, and all of the above is also incorrect because you are applying the the Newton's second law is saying that F equal to m dv dt, right? So that means the only changing variable in this quantity with respect to time is the velocity, which is v. So that is what that changes for that object. So velocity. Now question number 3 is about applying Newton's second law of motion to decide in which of the following cases a particle will experience an acceleration. More than one answers can be correct. Okay, so Newton's second law again you have to apply, and you have to decide in which of the cases the particle will experience an acceleration. First option is that a particle moving in a circle with a constant speed. Okay, so first of all, let me give you the idea that what do they mean about the particle will experience an acceleration. Do you understand what they mean by the particle experiencing an acceleration? What does acceleration mean, or how to experience that the particle is feeling acceleration? So if you just go by the scientific terminology, acceleration or a vector is basically simply acceleration. Let me write down. So acceleration is simply a vector, which is nothing but the rate of change in velocity. So dv by dt. This is also a vector quantity, means it has magnitude and direction, and velocity is also a vector quantity. So for an object, if its velocity is changing with time continuously, so then acceleration is felt by that. Like you are sitting in a car and the car is moving, right? So its velocity that is changing with time. It can also like move with a constant velocity. In that case you will have no acceleration, but whenever you are changing the like velocity or changing the you are speeding up or slowing down, then basically what you are doing, let's say for slowing down, when you are pushing that brake, so you are suddenly changing its velocity to a different value or to a slower value. Velocity magnitude is decreasing, so that means your velocity is not getting being constant, but it is decreasing over time. Or in the same sense, if you are trying to speed up the car, what you will do is that you are basically increasing the or letting the velocity to increase with respect to time. That means your dv by dt is non-zero, or whatever your velocity that you are moving in is continuously increasing or decreasing. It is not being constant. So then you will say that you have an acceleration that you can experience. But if you, let's say you are sitting in a car that is moving with a constant velocity, that is neither it is slowing down or neither it is moving faster, it is moving at a constant velocity that is not changing with time. Okay, so in that case we will say that the acceleration will be 0, because then dv dt will be 0, right? So if your t is changing, time is changing, you are going like moving across time, and but the velocity is constant, the velocity is not changing, you have fixed the, let's say there is a mechanical system that you want to always move in a constant velocity, so that is basically controlled by your by some machine, and you set the velocity to be constant. Like say you want a wheel to move in a constant velocity, rotate in a constant velocity. Not I will say that do not take the idea of the wheel, rather take a like simple object, and you want to like there is a, let's say, toy model of train, and you want to set the velocity of that train to a constant velocity. So its speed is not changing, it is moving in a straight line. Then with time the velocity is not changing, because velocity consists of both value or the magnitude and the direction. So if the car is moving or the train is moving in a straight line, then its direction is not changing. So one thing is sure, the direction not changing, the velocity vector, and then its velocity, then its speed value, that is the magnitude of the velocity, is also constant with time. So then we will say that the whole velocity vector is a constant. So your then dv by dt, the rate of change in velocity with time, will be 0. That means your acceleration or a vector will be 0. So then we will say that this object that is moving with a constant velocity in a same direction, that constant speed in a same direction, that will have a 0 acceleration. But What was the question? Yeah, so which one experiences an acceleration, you have to understand. Okay, so this, in this case, the object will be experiencing an acceleration when the velocity is actually changing with time. So a is non-zero if velocity is changing with time, but a equal to 0 if velocity is constant or not changing with time. But remember that even if acceleration is 0, you cannot always guarantee that the object is at rest, because the object can be moving and still it will have 0 acceleration, given the condition that the velocity in which the object is moving should not change its value or the direction over time. So in that case, you will see that there are objects which are moving at a constant uniform speed in a constant particular direction. So it is not at rest and still its acceleration is 0. So now once you have this idea, let us go to our question. It says that option number 1, a particle moving in a circle with constant speed. So will it have acceleration? Will it experience an acceleration? Give answer by Newton's second law of motion. Particle moving in a circle with constant speed. Now most people can make a mistake in this case, that after reading that there is a constant speed mentioned, they will think that, oh, velocity is then constant and then dvdt is 0, which makes a equal to 0. That means it will not experience any acceleration. But this is not true, because in the earlier class also I discussed that speed and velocity, those two are very different things. Means that velocity is a vector quantity, v for vector, and speed s for scalar. Speed is a scalar quantity. So whereas speed of that particle is constant when it is moving around a circle. So let us draw a circle like this, right? And let's say a particle is there, which is this, and it is basically moving around this circle, and its speed is constant. So it is moving at a constant speed. That means, let's say just for the sake of it, for the heck of it, I am not saying that this is the absolute value, but let us say this is moving 5 meter per minute. It has a fixed speed that it is moving 5 meter per minute, let's say. That means it is moving across this, its speed is constant. But the real question is the velocity constant or not? So you will see that velocity is not constant in this case. So even if speed is constant, velocity is not constant. Why? Because velocity has both magnitude and the direction. So let's say v cap is the unit vector which denotes the direction of velocity at each particular moment. Denoting direction of velocity at each particular moment, right? So your when it is moving around the circle, so what you will see is that at every point its direction of moving is getting changed. That means here at this point, when it is on top of the circular thing, then its velocity tangentially, always velocity will act tangentially on top of a circular thing. So on this point its velocity is tangentially this directional, and at this point its velocity is tangentially this directional. Then at this point its velocity will be this, if it is moving, let's say, anti-clockwise, I am assuming. So at this point its velocity will be this. Every point it is acting around along the tangent of that circle. So even if the speed, or which in other words is the magnitude of the velocity vector, or the magnitude of the velocity vector, that is v vector naught, is constant, but the direction of moving or the unit vector denoting the direction of velocity v cap here is always changing at each point on the circular surface, and the direction will be always along the tangential direction at that particular point. So as I have showed you, at every point there can be a tangent direction drawn, and the velocity will be directing along this direction. Okay. Right. So at each point the velocity direction is getting different, and the velocity being a vector, both of things will matter, like magnitude and the direction. So even if the speed or the magnitude of the velocity is constant, but because the direction of velocity vector is changing, that means the velocity vector itself as a whole will also be changing. So in this case, the velocity vector is not constant in time as it is moving on the circular track. Rather, it is changing with time. So dv dt is non-zero if v is not constant, or acceleration is non-zero. That means it will experience some certain finite acceleration. So the first option given to you was that whether it will experience an acceleration for the particle moving in a circle with constant speed. The answer is yes, it will experience an acceleration. The second option is a particle moving in a circle with variable speed. So it will obviously experience acceleration, because now you can see the speed is also variable. That means while moving in a circle, it is not only changing the direction of the velocity vector, but also it is changing the speed at every point. So the magnitude of the velocity vector is also changing, so v is also changing. So now also dv dt is non-zero and the acceleration is non-zero. So a non-zero for both of them. Third is a particle moving in a straight line with constant speed. Now this is another thing that is to be considered, that this is actually your correct answer, that okay, so it is saying that in which of the cases the particle will experience an acceleration and which of the cases it will not accelerate is basically not what you have to mark here. So this case I will first give you the answer that this will not experience any acceleration. Why? Because right now the particle is moving in a straight line. So if this is a flat surface, it is moving always in a straight line in a particular direction like this, and the constant speed is also constant. That means your both of the things are taken care of. The magnitude of the velocity, the vector, that is the speed, is constant, and the direction is always fixed in a particular direction when it is moving in a straight line motion. Right? So both the magnitude and the direction, that is a unit vector of velocity, is constant, not changing over time. So then it will have zero acceleration, because if v is constant, then dv dt equal to 0, or the acceleration will be equal to 0. So the third case will have no acceleration. The fourth case is that particle speeding up or down while moving in a straight line. So this is also very clear that this will experience an acceleration, because the terminology is very simple, that even if it is moving in a straight line, that means the velocity vector's direction is not changing, is constant, but here the magnitude itself is changing because the speed is moving up or down. So the magnitude of the vector quantity is not constant, it is sometimes up, sometimes down. So that makes the whole velocity vector not constant. So then your acceleration, which is the time derivative of velocity, is non-zero. So only correct answers where the particle will experience an acceleration are 1, 2 and 4. So this is your correct answer that you have to mark. Right. So now question number 4 is about, suppose P denotes the momentum of a particle and F is the force acting on it. So the total momentum change due to the force F is P1 vector minus P2 vector. Apply Newton's second law of motion and identify the image that describes the relation between the directions P1 vector minus P2 vector and F vector correctly. So you have a particle. Okay, so particle has a momentum P and you are applying a force F on that particle. Now Newton's second law they are saying you have to apply. So Newton's second law states that F vector is equal to dp vector by dt. dp is the change in momentum in dt time. So the change in momentum vector dp vector is simply F vector times dt. Now dt is just a change in time or a small infinitesimal amount of time, so it has no direction, right? Time has no direction, but the force and the momentum change vector has both directions, and they are on opposite sides of the on two sides of the equal to sign. That means these two vectors will have the same direction. So direction of the two vectors are the same on two sides. That means F vector will be parallel to the direction of dp vector, which is the change in momentum vector. So in this diagrams or in this question, the change in momentum is given as p1 minus p2. So this is basically your effective dp vector. dp vector is p1 vector minus p2 vector. And so as per this Newton's second law, your dp vector has to be parallel to the applied force F vector. So which one of these four diagrams cover that? So if you see that this is the only correct option, because here this P2 and P1 minus P2 is in this direction and force is in this direction. So they are parallel to each other. Okay, so that means this thing is correct, or the second law is correct. But on the other three cases, you see that P1 minus P2 is on this direction and P2F is on this direction. So this is not following the second law. Then this is also not correct, because it is on a certain direction. This is on the other direction at some other angle. So again, this is incorrect. And here also, force and P1, P2 are in completely different directions. So only the correct answer will be option number A, where the F vector is parallel to the P1 minus P2 vector. Right. Now question number 5 is that a tennis ball of mass 100 gram traveling in the plus x direction with a speed of 72 km per hour hits a wall and rebounds. After the collision, the magnitude of the ball's momentum is nearly the same, but the ball is traveling in the minus x direction. Then apply Newton's second law for of motion and compute the impulse in kg per meter kg into meter per second that is applied to the ball by the wall. So this is somewhat of a mathematical question after all these conceptual questions, and you are given a tennis ball that has a certain mass m 100 gram. It is moving along plus x direction, which is that it is initially moving along this direction, and then while going in this direction it hits this wall that it hits, and then it rebounds back, or it comes back, and it is said in the question that it comes back in the same momentum of this initial momentum, but now its direction has been flipped, because earlier it was in plus x direction and now it is in minus x direction. So even if values are similar, but the direction has been flipped, so this both vectors are different. So now Newton's second law, you have to compute the impulse. So you know that Newton's second law is F equal to dp by dt, right? Or dp vector is equal to F times dt. So the definition of impulse is that impulse is the change in momentum for a force applied to that body for a certain infinitesimal amount of time t dt. So this is the rate of change in momentum is nothing but basically an impulse term. So this is the impulse equal to dp vector, which is basically your F times dt, right? So you have to, using this law, you have to calculate what is the impulse for this case. So first of all, here there is a ball of mass 100 grams. So this is a ball that is moving in this direction. This is the plus x direction, okay, and this opposite direction is the minus x direction. So now this is moving with a mass m, and the velocity in plus x direction is equal to v equal to mod of v times x cap. X cap is the direction of the velocity and v is the magnitude of the velocity. And this magnitude is basically the speed value for the velocity is basically 72 km per hour. which is basically, if you take your calculator and just convert it into meter per second, so meter per second, because the final answer they are asking you is in terms of units of kg meter per second, so you have to convert it back into meter per second. So kilometer per hour is basically 72 into 1000 meter by 1 hour is 3600 second. So you have 72 into 1000 divided by 3600, which is basically 20. I can see that this is 20 meter per second. This is the velocity. Now after getting rebounded or bounced back from the wall, it moves in a minus direction. So it is, instead of x cap, it is minus x cap now. And so it is initial momentum of this ball is pi vector is equal to mass was 100 gram, right? So 100 gram you have to convert into kg because the option is given in kg. So m equal to 100 gram is basically 0.1 kg. So p vector initial momentum is 0.1 kg into v initial velocity, which is 0.1 into 20 in the plus direction, kg into meter per second. So this is 2 kg meter per second. Now while moving, rebouncing back from the wall, its momentum is pf equal to m pf vector, which is 0.1 kg into minus sign, because now the velocity direction has flipped, but the value remains the same, that is minus 20 meter per second, which is minus 2 kg into meter per second. Now what is the impulse? Impulse you know, because this is simply dp vector. Dp is nothing but pf vector minus pi vector. So the final is minus 2 x cap and the initial was minus of 2 x cap. So the whole thing becomes minus 4 x cap. So this is the impact, that is minus 4. And so the question that you are giving, this is an answer. So this is in minus 4 something order, you will see. Now question number 6, that consider a force F equal to 2t in Newton is acting over a time interval delta t starting from time t0. Which of the following statements is true about the impulse of the force? So basically your force is given by this expression F equal to 2t, this is in Newton, and this is getting applied for a time interval of delta t, which starts from t equal to 0. At the initial state, time is also 0. Which one of the following statements is true about the impulse of this force? So you know that formula of impulse is basically dp is equal to f dt equal to 2t So basically you are changing from t equal to 0 to t equal to delta, right? So this will be your integration limit. Now if you have to simply do the integration, this is basically 2t squared by 2 from delta t to 0. So this is basically delta t squared. So if dt is 2t dt, that is 2t squared by 2, and from 0 to delta t, it is simply delta t whole squared. So now the impulse, you have to choose from the 4 options. Impulse remains finite and non-zero as delta t tends to 0. This is not true because impulse equal to delta t whole squared. So the impulse. So if delta t tends to 0, then impulse also tends to 0. So this is incorrect. Then impulse tends to 0 as delta t tends to 0. This is correct because as delta t tends to 0, this is going to 0. Impulse remains finite at delta t going to infinity. So this is the second case, that if delta t tends to infinity, then of course this impulse is proportional to delta t squared. So this impulse will also be moving to infinity. So impulse remains finite as delta t tends to infinite is incorrect, but the fourth option is correct, that impulse tends to infinite also as t tends to infinite. So this 2 and 4 are the correct options. So 2 and 4. Then question number 7 is that according to Newton's first law of motion, which of the following statements is true about the motion of an isolated test body? First of all, what is Newton's first law of motion? It basically says that if you have an isolated body and you are not applying a force on the body anyhow, so until and unless you apply a force, the body will not change its velocity. It will like keep moving in a constant uniform speed in a straight line motion. Okay, so or it can be in rest. It can be either at rest, or it will have to be moving in a constant velocity along a straight line. This is the Newton's first law. Basically that means that if there is no force acting on the body, then there will be no acceleration, or a will be equal to 0, because force is mass times acceleration. So if force is 0, then the acceleration will also be 0. So in that case, because the acceleration has to be 0, so even if the velocity is non-zero, that means the car is moving or the object is moving, but the rate of change of velocity with respect to time will have to be 0, because dv dt is equal to a, and if a has to be 0, then dv dt has to be 0. So this is the Newton's first law. Okay, but there is another thing, is that the first law always holds true only for inertial frame of reference. This is a very crucial condition for the first law, is that whenever you are saying that the particle or the object is moving with a certain velocity or in a certain direction, then the first question that comes to our mind is that with respect to what? So everything in this around us is measured with respect to something. So there has to be some reference with respect to which we are seeing the particle to move, or the shoe to or the body to move. Okay, so based on that, it has to be an inertial frame, right, as I said. So the first option was that it experiences physical interactions such as gravity and electromagnetic force. This is obviously not true, because as you are saying, this is an isolated test body. Isolated means it is isolated from the whole environment, so it will not have any force effect from any parts of the environment. It will not have any force from gravity or electromagnetic force. Although it is an ideal case, in reality this is not probably possible to do totally, to eliminate or create an isolated system. But for theoretical purposes, this is incorrect, because the isolated object will not experience any such force. Then a bird flying through air is an example of isolated test bird. This is also not correct, because a bird is actually flying through air, so it will always have some drag force of air on the bird, and other forces will be there. Mostly from air the forces will be applied on the bird, so it will not be an isolated body on which no force is applicable from the environment. Then option number 3 is that in an inertial frame of reference, the acceleration of that isolated test body is 0. So this is actually Newton's first law. This will be true because so question number 7 will have option number 3 correct finally out of the first two, because as I said, the Newton's first law is only valid for inertial frame of reference. That means the frame of reference with respect to which you are saying that the test body or the isolated test body is motion you are observing, so that has to be an inertial frame of reference. So your reference frame should not be moving with an acceleration or with a velocity changing with time. Either it should be a rest frame, or it should be moving with a velocity at a constant uniform velocity, or that means its direction or the velocity value or the magnitude both should be constant in time. Then only you will say that this is an inertial frame, and based on that, with respect to the inertial frame, the acceleration of the isolated test body will also be 0, because Newton's first law says that there is no force applied on that object. That means the acceleration will also be 0. So if force is 0, no force is applied, so then acceleration will also be 0 because F equal to m times a. And this is only valid for an inertial reference frame where the reference frame is itself either static or it is moving at a constant uniform velocity without changing the direction and the speed of that velocity. Okay, so this is correct. And the fourth option was that to experimentally design an isolated test body on the earth, it should move horizontally to cancel gravity. First of all, this is incorrect because to make the test body isolated, it should be free from any kind of interactive forces from all over the environment. So even if you may think that the isolated test body is feeling the only kind of force from the earth because of the gravitational force or something, then it is not correct, because even if you move the object horizontally, that means the vertical force component is not present that may come from the earth, but then it will only cancel gravity, but it will not be able to cancel the horizontal movement. During the horizontal movement, whatever contact force it faces, let's say it is moving on a horizontal flat surface, so then there will be always an interactive force between that surface and that body, which is non-zero. So basically this is not experimentally possible to design like this, that the body on earth is moving horizontally to cancel gravity. Then it will not be an isolated test body, because anyway there will be a interactive forces coming from the contact of the body with the surface or with the earth. So in that case it is not it should not be called an isolated test body. Okay, so now question number 8 is that a reference frame is a coordinate system plus a clock to measure the motion of an object. There are 4 examples of reference frames below of which are below of which 2 are inertial reference frames. Identify them. So out of these 4 options, you have 2 frame of reference which are inertial reference frame you have to identify. Now it is said that the first reference frame is coordinate system plus a clock to measure the motion of an object. So first option is that the rest frame of a train moving at a constant speed on a straight track, that is, in this frame the train will be at rest. So this one will be an example of an inertial reference frame. Why? Because the rest frame of the train is moving at a constant speed on a straight track, that is the frame of the train will be at rest. So basically the train's frame is rest frame, that means it is moving with a constant speed, or it has only the magnitude of the velocity that is changing, but the direction the magnitude of the velocity that is constant, and the direction is always also constant. So in this case the velocity is constant, velocity is not changing with time. That means it will be a inertial reference frame. That was the main idea of an inertial reference frame. Now the second one option was that the rest frame of a lift falling freely down the earth, that is, in this frame the lift will be at rest. So this will not be an inertial frame of reference example, because the rest frame of the lift is falling freely towards the earth. That means it is actually being accelerated gravitationally when it is moving freely down the earth. So this frame, in this frame the lift will be at rest. It is not true, because it is itself not an inertial frame of reference. It has an acceleration because it is moving in the gravitational acceleration in action. So that is why this is a non-inertial frame. So this is non-inertial. Question number 3, option number 3 is that the frame fixed to a rotating merry-go-round, that is, in this frame the merry-go-round will be at rest. So that is also not an example of what is that? Is the inertial frame of reference, because here the merry-go-round is itself rotating. Okay, so it is not at rest or either moving at a constant speed. So basically because of that, this is a non-inertial frame of reference. And the fourth one is that the frame of the rocket moving in. Okay, so I did not put the actual sign. So basically the first one was a inertial frame of reference, but the second one is not an example of inertial frame of reference. Third one is that it is fixed to a rotating merry-go-round, that is the frame of the merry-go-round will be at rest. So this is not also correct, because when it is moving, the whole thing is moving, the velocity is non-zero, and the velocity is some finite value which is not changing with time. Therefore the acceleration will be uh, okay, so I think I have confused the whole thing. So basically your option number 1 and 4 I think will be correct. The rest frame of a rocket moving in a deep space with constant velocity. In this frame, the rocket will be at rest. So the first and fourth option will be correct, because on the first option the train is moving at a constant speed. That means the reference frame of the train uh, has a constant magnitude of the velocity, and it is said that it is moving on a straight track. That means the velocity direction is also not changing. That means combined by the magnitude and the direction, the overall velocity vector is not changing with time, or v vector is equal to constant here. So dv dt is equal to 0, or the acceleration is 0. That means it is an inertial frame of reference. This is true. Then the rest frame of a lift falling freely toward the earth, that is, in this frame the lift will be at rest. So the lift is actually falling down toward the earth, so it will be acted by the gravitational force or acceleration g, where g is equal to 10 meter per second square in SI unit. So the lift is actually falling down by this acceleration. Its falling down direction is constant, velocity direction is constant, but the value of the velocity is changing, because there is a certain g which is acting over time, so that the velocity is not constant. So here, because there is a non-zero acceleration, so it is a non-inertial frame. Then option number 3 is that the frame fixed to a rotating merry-go-round, that is, the frames of the merry-go-round will be at rest. So whenever there is a merry-go-round and the frame is fixed to that, so the merry-go-round is rotating. That means with respect to that, if you want to see, then it has a certain acceleration, or a is non equal to 0, because it is moving in a particular direction, is getting changed with time. So a is non-zero, and as a result this is also a non-inertial frame. And the fourth result is that the rest frame of a rocket moving in deep space with constant velocity. So the rocket is moving in space, its velocity is constant. That means its direction and the value of the velocity is constant. So the rocket will be at rest. So that is the inertial frame of reference, because when the frame of reference itself does not have any acceleration, or a is 0, that means in this case it is also a inertial frame of reference. So the two inertial frame of reference options are 1 and 4. Okay, so with this I think we solved all the problems from this week's tutorial. So follow this part. If you have any problem, just ask me in the next class, and we'll meet in the next class regarding the assignment of the next week, right? Okay.